Alright, I've got a lot of stuff to go over today. Up on the screen I've got what we left off with in the last video, which is our 7-segment display just cycling through numbers 0 through 9 with about a second pause in between each change. The problem with this though is our code is not very good. It's got an issue with it. And let me get rid of that. Let's take a look at our code and see what the issue is. Again, same file as last time. If you scroll down to our main loop and we take a look at it, it has to do with how we implemented this pause. To implement a pause, the simplest way was to use a for loop that literally does nothing and essentially just wastes time. Now this is a huge problem because most of the time when you're building something with a microprocessor, you can't afford to just waste time. Usually you're going to be pulling in sensor data or performing calculations using that data or handling inputs from the user or displaying values. So you never want to just waste clock cycles. You always want to at least give your processor the availability to do something. So this kind of implementation is not good. And another disadvantage it has is, let's say, well, okay, this value gives me close to a second pause, but it might not be exactly a second pause. So let's say there was something more timing critical that we wanted to do. If we wanted to have it execute exactly on a second, we could change this value to get us very close. However, what if there was another part to this loop that took longer than, or what if this loop was more dynamic and there were other functions above this for loop that how long it takes to execute their code might change. So let's say you had a bunch of if statements in a function and each of those might have their own for loops inside them, or something that takes time. Depending on how the if statements execute, that block of code might take longer to execute or shorter, and so the total time to execute our while loop might change. The issue with that is if this is close to a second, given whatever this whatever the functions above it take to do, like total, if the other functions take longer or shorter, then the total time is not going to be a second. So our pause is going to change with time, and that might not work for some applications. So it would be more handy if we had a solution that allowed our processor to not waste time, but still give us a second pause in between display changes, and also that was more precise in that it's going to execute on the second every second. Well, today we're going to be doing that using timer 1. It's a built-in timer in, I think, every PIC32, but we're going to be taking a look at it, of course, on our 250MX250F128B. So we're going to have to look at some documentation briefly just to get a good intro and know what we need to set. So if you go ahead and Google PIC32MX250F128B, smash that, and look for the product page on Microchip. Then go down, click Documents, and then scroll down until you find the reference manual. And I've shown this in previous videos, but I wanted to show it again now that I have internet. But today, like I said, we're going to be looking at timers. So we're going to grab that. It's going to pop up this PDF for us, which is nice. But we're also going to be needing the documentation for oscillators, because the timer is based off of the oscillator. So we're going to click that. Okay, let's take a look at the timer. This is a good document, and I suggest you read through it. I've read through a little bit of it. I always just skim just to get a good general idea of what I'm doing or what I need to do, and then as problems come up, I tend to go back and try and dive in deeper. But I'm going to point out a lot of things in the document today, but I'm going to try and keep it as brief as possible, because Like, I don't want these videos to just keep going on, and I'm trying to get you through it so you don't hate me for watching this video. But I'm going to point out what we need to do for basic usage. So today we're going to be using timer 1, which is a type A timer. And these have a few things about them that are nice. This asynchronous timer counter with a built-in oscillator, we're not going to need to worry about that today, nor are we going to be putting anything into sleep mode. We are going to have to worry about this prescaler, and I'll point out what that is in a second. And then down here is a table comparing the two further. You can use a secondary oscillator with timer 1, which is a type A timer. You can also use an asynchronous external clock. I think you can use external oscillators with most timers, but we're not going to be doing that, and I don't have any intention of using an external oscillator at this point. Again, synchronous external clock. One thing to point out with the type A timer is it has a 16-bit counter register. If that doesn't make sense to you right now, that's okay. I'm going to explain that in a minute. But notice how we're on a 32-bit architecture, but it only has a 16-bit counter register. The type B timer, which we're not dealing with today, has a 32-bit register, but again, that's for another day. It's a gated timer, and it doesn't have a special event trigger. So let's take a look at this diagram. A couple things that are very important to point out are down here. This input signal is our peripheral bus clock, which I'm going to explain in a second, but just know that in order for our timer to execute, it takes a clock input, and that clock just keeps ticking and ticking, and as it ticks, what our timer does is it increments its I forget which one it is. Let's see. It's either the PR1 or the timer 1. I really should know that off the top of my head. Okay, yeah, it's going to increment this timer 1 register and compare it to this PR1 register. And so what that does is, let's say we know what frequency our peripheral bus clock is ticking at. If you know what frequency it's ticking at, you know how many ticks it's going to take in order to reach a certain number. So, for example, let's say we were operating at, well, let's go convenient. Let's say we're operating at 500 kilohertz, and I want it to last exactly a second, but I have a prescaler of 8. So what that would do, here I'll go ahead and get to it, calculator. So let's say our peripheral bus clock, so this clock input signal down here is 500 kilohertz. There we go. And this prescaler up here, this software selectable prescaler, crap, need my calculator back. Let's say we had that set to 8, and what the prescaler does is it takes this peripheral bus clock, oh, maybe I should just point that out. And it's going to divide down, so it's going to take the peripheral bus clock and divide it down by whatever value we set it to. So if we had it set to 1, it would take the peripheral bus clock, divide by 1, and you're still left with whatever the peripheral bus was set at. But we're going to divide ours by 8. So this speed divided by 8, and that gives us 62,500 kilohertz. That's how fast this timer is going to be incrementing by. So once every 62,500th of a second, it's going to increment our timer 1 register. So if we want something to last 1 second, what if we told it to count up to 62,500? Since the clock's ticking at a speed of once every 62,500th of a second, if we count up to 62,500, we're going to achieve that value in 1 second. I hope that makes sense. But so if we set our PR1 register to 62,500 and we want to count up, and every 62,500th of a second we increment this by 1, in 62,500 cycles, these two numbers will be equal. This timer 1 would reset, and then you start all over again. So the basic usage of our timer 1 is you have a clock input, which gets prescaled, and then, oh, you know what? I'm being so stupid here. Sorry. The proof of bus clock comes in and then hits this prescaler, which then comes up here, and you can choose synchronous or non-synchronous. And then that comes into the timer 1 and increments at each clock cycle. So again, peripheral bus clock hits the prescaler, comes in, and every whatever that new period is, or frequency, it's going to increment the timer 1 register. And when they're equal, it outputs an event flag and resets the timer 1 register. That's the basic operation. Okay, so then there's the type beat diagram. Again, we're not worrying about that, but we are worrying about our control registers. So today we're going to be using timer 1, so we're looking at this T1 con. And it's got a few important bits, and they're labeled in this document. So bits, I think it's, what, 15 down to 8's the on bit, and so on and so forth. And if you come down here, it gives you the timer 1 con type A register. So again, timer 1 is type A. But it goes through each bit as they're important. And for today, mainly you just need to worry about the on bit. So if the bit's 1, the timer's enabled, and it's going to be incrementing and resetting, just counting time. The other one that's going to be important is this TCK-PS, and that's our timer input clock prescaler. So again, we're going to be pulling in whatever the peripheral bus clock is and then dividing it by this number. And this number is represented by 2 bits, so you have 4 options. And if it's 0, 0, you get a division by 1. If it's 0, 1, you get a division by 8, and so on. Those 2 things are going to be very important to keep in mind later on. So obviously, if we knew what our peripheral bus clock was, if we knew what its frequency was, then we could perform all the calculations we want and have a timer 1 that would increment that would go off every 1 second. So what is our peripheral bus clock running at? Well, this is actually the interesting part. That depends. If you're using the PIC32 is very versatile in almost every way you can think of. But here we have a nasty clock diagram. You can give it external crystals, you can run off internal oscillators. There are so many options for whatever you would want to do with this microprocessor. Again, I'm just trying to keep this thing simple and not have to buy very many components. So today, we're just going to be using the internal oscillator, and even just the internal oscillator has a few settings you can do. But today we're going to be using, well, I'll show you. There's some configuration bits that you can set and get an idea of what your system's set up to. So unfortunately I've got mine open already. I'll show you how to get that. Basically you go to Window, then pick Memory Views, and then go to Configuration Bits. And it's going to pop up this thing in the bottom. And what you want to look at for today, if you scroll down just a little bit, you're going to see this FPLL IDIV. What the heck? Oh yeah, these are all our clock settings. Actually, scroll down even further and go to this FN oscillator, and you'll notice it says oscillator selection bits, and it's set to FRC div. So again, there's a bunch of different options you have for setting what clock you have. You'll notice here that we have an 8 megahertz FRC oscillator. So this is the built-in oscillator on the PIC32 MX250F128B. And it branches off a few things. So here it goes directly up to this FRC signal, which comes into this multiplexer, but it also has this, it hits this post scaler and then goes to FRC div. If you go back to those configuration bits, you'll notice that right now it's set to FRC div. That should sound familiar, but if you click on that, you have a few other options. So we also have just FRC, we also have FRC, PLL, and all these other options. I'm going to leave that on FRC div. But if you go back, well, there's our FRC div, and here's FRC. I don't remember what other thing I said, but like here's POS and XTPLL. If you look at these names, they should correspond with some of these names too. But for today, we're going to leave it set at FRC div. So what that means is I have an 8 megahertz typical, because internal oscillators might not be very precise, but I have an 8 megahertz clock that's going to hit this post scaler, and that is called FRC div. And then if you'll notice, it comes into this multiplexer. Yes, I think this is a multiplexer. But this gives us our CPU and select peripherals. So this is our system clock, and it even says so there. This is what like all of our processor actions are being based on. But then we come up here and we hit this post scaler, which is our PB div, and that gives us our peripheral bus clock. And you'll remember that's what our timers are going to pull off of. So if I knew what this frequency was, then I could tell you what the peripheral bus clock is. Well, we know we're using FRC div, and that's based on this 8 megahertz, but it's going to get divided by a little bit. So let's go back, and you'll notice, oh, well, here's a piece of information. This PB div, that should look familiar because it's right here. It's our post scaler on our system clock, which is going to give us the peripheral bus clock, which is what we want. And that sucker is currently set to a division of 8. So whatever our system clock is, the peripheral bus clock is going to be 1/8 of that. But we still don't know what the system clock is, because we know we have an 8 megahertz internal oscillator that hits this divisor before it becomes what we know, what we're using. So what is this guy? Well, oh, I want this document. If you scroll down to control registers, you'll notice in here we have this FRC div, and that's the same name we were just looking at. Scroll down, you'll see it right here, and here's all the different configurations you can go to. But look at this, it's FRC divided by 2 is the default setting. So since we haven't changed any of our configuration bits or set any of the OSCON bits, which is the register that controls the oscillator, everything's default. And therefore, if we take a look at this diagram, well, I know I have 8 megahertz coming in from my internal oscillator that hits that FRC div post scaler, which was set to a value of 2 by default. So we have 8 megahertz coming in. I'll do this just so you guys, just so it's easier. 8 megahertz coming in. Okay. Then I hit that FRC div, which was set to a default of 2, right? So we're going to divide by 2, and that gives us 4 megahertz. Then we come in here and we hit this second pulse scaler for the peripheral bus, and if you remember, that was set to a value of 8. So I'm going to divide by 8, and this gives us our peripheral bus clock frequency, which is 500 kilohertz. That should sound familiar because I mentioned that earlier. Alright, so now if we go back and we take a look at our timer, okay, we're just about there, but I need to point out one more thing. This comparator, if you remember, is a 16-bit register, or our counter register. So it's got a 16-bit synchronous counter right here. So what that means is we can only count up to the largest value of 16 bits. So if you go calculator, the largest unsigned value you can count up to for binary is 2 to the nth power minus 1. So it's going to be 2 to the 16th, since we have a 16-bit register, equals this number minus 1. This is the largest value that we can count up to. Since we're operating at 500 kilohertz, let me see if I can phrase this so it'll make sense. This is the largest value I can count up to. Since I'm operating at a frequency of 500 kilohertz, the period is going to be the inverse of 500 kilohertz, which is a lot less than 1 second. What is that? Let's see, 500 kilohertz. I think they have inverse somewhere. This guy. That's that of a second. And then if I times that by, oh man, I don't remember. So this is how often it's going to increment that register, this register. So, but since I can only count up so far, it was around 65,000. So bear with me here. It's not going to be exact, but it was around 65,000. So this is the highest value I can count up to, which is only 0.13 of a second. So because I only have 16 bits to work with and my peripheral bus is still operating at such a high frequency, the most I can count up to before it's going to reset and start all over again is about 1/10 of a second, which is going to be a problem if you need something that takes longer than that. And since I'm aiming for about a second here, that's not going to work. Luckily for us though, we have this other prescaler. So we have our peripheral bus clock coming in at 500 kilohertz, but we have this prescaler to work with. Oh boy. So 500 kilohertz. I could divide that by 1, which isn't going to help me. I could divide it by 8, 64,256. If I divide that by 8, that gets us to 62,500, which just off memory is really close to what the maximum value we can count up to in a 16-bit register. And if you take a look at that, 2 to the 16th minus 1, that's 65,535. So it is barely under it. So here's what I was going at before. If I have, since I had 500 kilohertz coming in, if I divide it down by 8, so 500 kilohertz coming in, divide it by 8 with that postscaler, or prescaler, this is my new frequency, 62,500 hertz. So if I take the inverse of that, this is how often I'm going to be incrementing. This is the amount of time it takes between increments of updating this timer 1 register. So now if I times that, so if I count up to 62,500, what do I get? I get 1 second. So if I set my compare register to 62,500 and use a prescaler of 8, then it's going to take 1 second for this timer to go off. It's going to have a 1 second period, which is exactly what we want. Okay, that's been a very long-winded thing, but we're going to finally get into some code, and hopefully this will make sense. So the first thing I need to do is initialize the timer, timer 1. To do that, there's a few things we need to set. If you remember from the data sheet, oh, that's my calculator. From the data sheet, I have this T1 con register, and that's going to have all the control bits I need. So if I come in here, first thing I'm going to do is do a T1 con, which is a known name, equals 0x 2, 3, 4, 5, 6, 7, 8. Since it's a 32-bit register, I did this just so we know that. This is a all this does is reset the timer, or reset timer 1. By default, when I do this reset, I'm setting this on bit to 0, so the timer is going to be disabled. And one benefit of that is while I'm initializing my timer, it's not going to start counting and screw things up. So first thing I do is reset the timer and turn it off. Now I'm going to set things that are important. So T1con bits dot TCKPS, and that's going to equal 0B01. And do you remember, or do you have an idea of what this thing's doing? Well, keep this TKPS in mind. That is this prescaler. So I know I need to set that to a value of 8. But if we remember, in order to set it to a value of 8, I need to set my register bits to 0, 1, because that's, since I have 4 options, it's going to be the second option in that value. So I used binary here of 0, 1, and that is dividing the peripheral bus clock by 8. Next thing I'm going to do is reset my timer 1 register to 0, because I don't want to start counting from anything else. I want it to go off every second, so I'm going to start at 0 just for an initialize statement. And then this PR1, I want to set that to 62,500. Oh, this initialize, whoa. Initialize the counter at 0. Sorry, I forgot to put that comment in. And then here we are setting the compare register to 62,500. And this is to give us a 1 second period for timer 1. I'll just spell all that out. Okay, and then the last thing I'm going to do is do T1con bits dot on equal to 1. So this last statement just turns, whoa, need to put my comment, turns on the timer. Okay, and that's all the code you need to do to set that up for this example. Again, the 62,500 number, if you remember, just to go over it one last time, I'm setting this register, which is going to be compared to the current value that I'm counting. And since I have my 500 kilohertz peripheral bus divided down by 8 to give me a new period or a new frequency of 62,500, if I count up to the inverse of that, or if I count up to the same value, it's going to be a period of 1 second. I hope that makes sense. But that's where the 62,500 came from. Okay, so now down here, I'm not going to need this for loop anymore. But this last counting stuff, I only want to increment things once every second. So what I'm going to do is if my timer 1 register, TMR1, is equal to 62,500, so right before that thing resets, then I'm going to do all this stuff. So I'm going to cut that, paste it here. Oh boy. Fun, fun, fun. Fun for everyone. Okay. So I'm going to start loading that guy. And it's going to start programming. There we go. It's programming up. Okay. And so now it's still it's doing the exact same thing it was before, but the code is significantly different and its functionality is significantly different. Mainly, if you'll take a look at the while one loop, Notice that this if statement only executes every time this timer 1, so that register that we're incrementing with the timer, this code only executes once a second, but the rest of this executes just all the time. So really, the display here, our 7-segment display, this guy's getting refreshed at, well, probably close to whatever our system clock rate is. So for all the gamers out there, the FPS of this bad boy is probably close to 400 megahertz, which is crazy if you think about it. But again, our code, it's not hung up right now. It could do so many other things because we're not just waiting with the useless pause. Using the timer 1 has allowed us to do a whole bunch of new things, and I know this has been a very lengthy video, so hopefully it made sense. Next video, I think I'm going to go into using interrupts, specifically the timer 1 interrupt, and maybe a button interrupt. We'll see if I get there. And I'll try to explain what interrupts are and what their advantage is. So hopefully this made sense. Hopefully you learned something, and I'll catch you later.